Our first speaker today will be Dr. Joe Maja. Dr. Maja is a research sensor engineer at Clemson University's Edisto Research and Education Center. His main work has centered on developing sensor automation technologies for South Carolina farmers and Clemson's research scientists. He is currently in charge of the sensor laboratory at the center, where the technologies he develops are fabricated. The sensor laboratory is a unique laboratory in the center where design and fabrication of electronic modules and its enclosure can be manufactured. Prior to his work at Clemson, he worked as a research engineer at the Eagle Flight Research Center of Embry-Riddle at Aeronautical University in Daytona, Florida. His work with the Eagle Flight Research Center was in the area of development of automation for manned aircraft. Dr. Maja has developed several different technologies, and you can find examples at his website, which is listed on the bottom of your screen. In this segment of the webinar, Dr. Maja will report on sensor integration for UAS flight controllers. Before I pass the microphone to Dr. Maja, I would like to add some personal comments. Dr. Saraswat and I have been fortunate to have collaborated with Dr. Maja since 2009. Dr. Maja was critical in bringing UAS into our collaborative research efforts. Our situation clearly demonstrates that research efforts using UAS are most successful when it includes a team with a diverse skill set. As you will see shortly, someone with Dr. Maja's skills is critical to your team. My second comment about this next segment is how it illustrates how diverse the UAS learning network's topics have been. Up to this point, we have focused on flight planning and applications, but this is really our first presentation focused on sensor integration. Now, I'm very delighted to turn the program over to Dr. Maja.
Thank you, Jim. Good afternoon, everyone. Thank you for having me here. Again, my name is Joe Maja, broadcasting at Edisto Research and Education Center in South Carolina. We are located at 64 Research Road in Blackville, and as what most of our visitors said, we are 2 blocks away from the middle of nowhere here in South Carolina. So this is my presentation today, sensor integration for unmanned aerial vehicle. This will be the outline of my presentation. I will start with my current collaborators and will show a little bit of my work on flight dynamics at the Eagle Flight Research Center in Daytona, Florida. I will also present some of the video tutorials I created since 2010, and we'll go through the main presentation of sensor integration. I will try to present both dependent, sometimes referred to as shields, and module-based, and this is mostly what you will find in the market. I will also present an example for each of this setup. Then I will try to briefly discuss an example interface where we interface these available sensors to our UAV or UAS flight controller. Though this example is very specific to one flight controller, the idea of connecting these sensors is a bit general. So there is a chance that you can actually use the same setup on your UAV. I will present the general setup of having a feedback and a non-feedback connection, and we'll end this presentation with some sensors that you might be able to integrate on your UAV. So I have currently 2 industry-based collaborators, the Skybridge UAS, which is located at Greenville, South Carolina. Their company is geared towards providing services for precision and coastal patrol and oil gas pipeline inspection. As you may well know, their company is building their own fixed-wing UAS, including their military-spec autopilot system. So contrary to what you normally see or read on most of these UAS companies in the US, the other one is the AMS Columbia, which would like to create a spin-off of their current services as aircraft maintenance to UAS for precision agriculture. So my role for this company is to help them on their sensors, which they can use under different applications. I also work with Imbrapa Informatica Agropecuaria. I'm not sure if I pronounce it properly, but in English it says Imbrapa Agricultural Informatics in Brazil. This is the Department of Agriculture in Brazil. My point of contact is Dr. Joao Camargo Neto. Among other things, I also provide support to the different research scientists, to the different research centers of Clemson University. I have an ongoing collaboration with USDA, Agricultural Research Services at Florence, through Dr. Todd Campbell. And lastly, I also work with Dr. James Rubens from the University of Arkansas, our moderator today, looking at inventory using UAS. Our last work was last year with Dr. Matthew Chappell of the University of Georgia. So this is my project with the Eagle Flight Research Center, the research center of the Embry-Riddle Aeronautical University located in Daytona, Florida. Our task in here was to measure the flight dynamics of a modified Cessna 186. I designed the main board and the sensor connector board as shown on this slide. This board was designed to log up to 20 different sensors in real time. It was designed in mind that it will be easy to reconfigure, which means you don't need to change the firmware if you need to change the sensors or the baud rate of the sensors, and make use of several voltage divider to cover sensors which has a different voltage source requirement. And also it comes with a terminal debugger. I started working with UAS since 2009, building our own UAS at the University of Florida as a postdoc of Dr. Reza Izani. In the course of my work with UAV UAS and also with building different automation technology, I created around 39 different tutorials in YouTube. Most of these tutorials were for UAV UAS sensors and calibration, transmitter switch assignment, triggers, and data export, and even testing the brushless motors. My latest tutorials to date are for using QGIS. I think, as you can see, I also created these visualizations of different information using Specialite. I saw that there is a huge information of uploading the different treatment informations on your trials with QGIS. So this tutorial was actually created with my work with Dr. Gilbert Miller, who is our fruit and vegetable scientist here at the center. I also have tutorials to do NDVI calculations directly to QGIS. And I think the most important thing is georeferencing if you don't have a ground control points when you collect your data. The tutorials I created were on the different projects I have for the past several years. And there's only the project staff have access to this. I believe I can send a link to anybody who might or who may be interested in these tutorials too, as long as you can send me an email and some information on what you are currently doing. Now, let's go to the main topic, sensor integration. So sensor integration is a huge topic in the areas of electronics engineering. Some of the important areas looking at the macroscopic performance of the sensors embedded to different materials. But in here, in this presentation, we will skip that and presume that our sensor is not foreign to our material. Instead, it is somewhat the same as the material, so we will not worry on the deterioration of the macroscopic properties of the sensor. Sensor as a special substrate can be embedded into another material, and only the important connections of the sensors are brought to a header connector or to whatever connector the designer created. This setup is what I call dependent or open, or for some others they define it as a shield. The setup as is will not work as it does not have the supporting electronics that comes with it. Here is a very good example of the GPS sensor that I created for our Bull Tracker project with Scottsdale. The other setup is what I define as a standalone setup. This setup comes with a complete electronics where the sensor is embedded. Complete means that the only requirement for this setup is simply the power source. Most, if not all, have their own micro SD, which stores the data. It also comes with debugger that you can use to connect to your computer for verification and configuration purposes. In this example, here, this is the SMD, the starts measuring device I designed on one of my projects here at the center. The system comes with micro SD, USB interconnectivity, and the only requirement is a power source. Here's an example of the standalone sensing modality, which are commercially available in the market. I think most of us probably have been using these different kinds of sensors. For one is the TetraCam, MicaSense. We have also the FLIR and the modified camera, where we actually modified the filter of this camera. And you can send your camera, if you have one, to these different companies here, www.maxmax.com, livepixel.com, or colaravision.com. Now, this is an example of how to interface a common standalone setup for UAV or UAS flight controller. Notice the trigger setup has an Optical Isolator, also called an optocoupler, or optical isolator. Sorry. In this slide, the Optical Isolator is the TCMT1106 from Vishay Electronic Company. The Optical Isolator is an electrical component that transfers the electrical signals between two isolated circuits. In this case, your connections to your flight controller here, and your connections to your sensor module here. Using light, so as you can see, there is no connection here. This prevents high voltages from affecting the system on both sides. In this case, I wanted to isolate the voltage source of the sensor setup and the flight controller. I cannot emphasize enough the importance of not messing up your flight controller with other electronic module you plan to attach to your UAV. So we can attach our sensors in two ways. One, without any connections to your flight controller, which is the best option, but then you don't have any way of checking if your sensors work while your UAV is flying. This is the attach and play sort of connection. The sensors has its own controller, and you simply let it run by itself. The sensor in this case may have its own built-in intervalometer. That's what I've shown here. That comes with it. So a very good example for this setup is a Canon camera running a Canon Hack Development Kit, or CHDK. This is a very popular firmware that actually run on top of the firmware of Canon camera. And it has its own built-in intervalometer program that comes with it too. So you can run that intervalometer and just attach it to your UAV and let your UAV fly. The sensor that runs on this setup actually just keeps on taking pictures by itself. So there is no connections with your flight controller. The second setup is the setup I'm currently using on our UAV. So it is connected to our flight controller using a small trigger board that I designed. As it is connected to the flight controller, I can either use the so-called WP event, which we call that as a waypoint event. What this means is that when I created different kinds of waypoints on my navigation, when the UAV goes to that waypoint, it will send a trigger to the sensor that I attached to my flight controller. The flight controller intervalometer is exactly the same thing as what you have on CSDK. You set the timing when your flight controller will send the trigger signal to your intervalometer, to your sensor. While the last one, the manual control, is basically, it is connected directly, your flight controller is connected directly to your transmitter radio, where you turn on the switch and it sends that signals directly to your sensor module. Now, why it was defined as a manual control? Because it will only trigger once you switch your transmitter switch that represent the connections to that sensor module. Now, here is an example of how to interface the trigger module to your flight controller. The most important thing about this integration is knowing the schematic of your flight controller. The pin highlighted in circle here is the actual header pins where the programmable output is connected. And if we refer this to the interface schematic, the edge pins, pin number 1 and pin number 5, are connected to port C2, referred to as PC2 here in the schematic, and port C3, referred to as the PC3 of this schematic of the controller. We assign this port to one of our transmitter 3-point switches. Notice on this assignment, I only assign PC2 to the 3-point switch located in the top right of my transmitter radio. So this is the switch that I assigned to this port C2. So 3-point switch means I have 3 different stages. I have off, I have SEQ, and then I have an on, which means it's always on. This is always off, and then you have sequence. The LED bar, like the image in the middle of this slide, represent the configuration of that switch to my trigger module. So each of the bar here represents 200 milliseconds delay, and if the bar is red, that means the port C2 or PC2 will be high for 200 milliseconds. If it is dark, as in this case, it means the PC2 is low or is connected to ground. So for example, setup, we have, so for this case here, we have 1 low, 2 high, 1 low, 2 high, and 1 low, which translate to 200 milliseconds low, 400 milliseconds high, and then 200 milliseconds low again, 400 milliseconds high, and 200 milliseconds low. This will, of course, cycle forever until you move your switch to either off or on. Now, controlling the sensor trigger can be divided into 2. Open loop, or what I define as the non-feedback system, or closed loop, which I define as a feedback system. Here is a very good example of a non-feedback and feedback control. For non-feedback, you basically send a trigger signal to your sensor module, and assume that the sensor module will start collecting data. This will work if there is no disturbances in between the sensor module and flight controller. Disturbances can be attributed to electronic noise generated from nearby electronic boards, and etc. The feedback setup has the same setup as the non-feedback, but there is another connection from the sensor module to the flight controller. This is the feedback connection which informs the flight controller that the signal has been received, the data has been collected, and that it is waiting for the next trigger signal. These provide a lot of advantages compared to its counterpart, as you have the ability to know that for one, your trigger went through. For second, you know that there is no problem with the sensor and flight controller module, as you will always receive a return signal. As promised, I'm going to end these presentations with two potential sensors that the UAV UAS community may find us useful. The first one, this is the first one, the FIR array 16x4 is a far infrared array for collecting temperature. You can find a lot of information from this sensor, this link provided. This is manufactured by Melixis and is currently being used by automakers to detect side collision detection. I built a board for this sensor when I was working at the University of Florida. The second one is a programmable tunable detectors. It is a point multispectral sensors from Infratech, where you can change the spectral band by changing the voltage to the sensor. So the only challenge of using the sensor is that it needs a movable reflector or a modulated reflector that will be located on top of the sensor. Again, you can find more information on the sensors at their website. What this means is that if you needed different kinds of spectral bands on your work, you only need to buy one and just change the voltage source for this one to get different bands. Before I end this presentation, let me acknowledge the people and organizations who are in one way helped and are funded my projects at the center. Of course, Dr. James Rubens from the University of Arkansas Cooperative Extension Service, who is our moderator today. Dr. Dharmendra Saraswat from Purdue University. I also would like to extend my heartfelt thanks to the South Carolina Cotton Board and to the National Institute of Food and Agriculture of USDA. Also to Clemson, to the different scientists who've been supporting me here, to the USDA ARS of Florence, and also to Imbrapa. Again, thank you very much. If you need to look at my website, you can find me at www.iad4sc.com, and my email address is jmaja@clemson.edu. Thank you.